Gravitational potential energy 2. A 68 kilogram person stands on Earth's surface. Earth has a mass of 6.0 times 10 to the 24th kilograms and a radius of 6.4 times 10 to the 6th meters. Determine the absolute gravitational potential energy stored in the person-Earth system. The absolute gravitational potential energy looks like that. Negative, and then G is 6.67 times 10 to the negative 11. As long as the other units are fine, we're not going to worry too much about putting the units in to our work here. One of the masses is 6 times 10 to the 24th. The other mass is the mass of the person, 68. And we're going to divide by the distance between them, which is approximately the radius of the Earth. Feel free to type that in if you want. When I did, I got this, negative 4.3 times 10 to the 9th joules. Potential energy is in joules. That came out negative. With regard to the person in part E, what does it mean that the potential energy we calculated there conforms to part D1? Well, this was in a previous video. This was in the video before this one. And in part D1, we said absolute gravitational potential energies are always negative. What does it mean that that's a negative number? It means that the person is bound to the planet and cannot leave. If you want to leave, you have to get enough speed going that you are going to overcome this. And that is the point we're going to make here in letter G. Determine the speed the person would have to attain in order to not be limited to the part F answer, in order to not be bound to the planet. We would need kinetic energy, which is always positive, that entirely offsets or cancels out the negative gravitational potential energy. We would need kinetic energy, which is always positive, that entirely offsets our negative potential energy. Now, way at the top of the screen, you can barely see it now, negative 4.3 times 10 to the 9th joules. That's how much kinetic energy we would need. 4.3 times 10 to the 9th joules. This person has a mass of 68 kilograms, we were told. How fast would that person have to be going? Probably you're going to want to use a calculator on this. This person would have to get up to a speed of approximately 11,000 meters per second. And it turns out that that speed is independent of the mass of the person. And you might say, what are you talking about, Mr. V? If I change this mass, that's going to change this speed. Well, if you change this mass of 68, that will necessarily have changed this number over here. And they change proportionally. So no matter what mass you have, this is the speed that you would need to attain in order to escape. And we have a name for that. That's actually called the escape velocity. Given that 1 mile is approximately 1,600 meters, if you're in track or swimming, you might know that a mile is approximately 1,600 meters. It's a little bit more, closer to 1,609, but this boils down to roughly 7 miles per second. And that's the escape velocity for any object from Earth.